All right, page 9. A water tank at Camp Newton holds 1,200 gallons of water at time t equals 0. So this is how much water is in the tank to begin with. During the time interval from 0 to 18 hours, water is pumped into the tank at a rate using W of t. So we know that this is a rate. This is rate per hour, gallons per hour. This is WT. This is going to tell us how much water is how much water is removed by that time period. It's only telling us how much it's in terms of gallons per hour for that particular hour. Okay. During the same time interval, water is removed from the tank at a rate of R of t, 275 sine squared t over 3 gallons per hour. Okay, we're going to need our calculator to enter this in, but if we were to enter this into our calculator in terms of either graphing it or in terms of evaluating it, how would we enter this in? Is there a feature that allows us to have that exponent sine squared of t over 6? You got to create bracket. Good. So we have to understand that this is a shorthand form. This is a way for us to write the equation or the expression without having to use as many brackets. But for our purposes, whether it's derivative or chain rule or even calculator, we have to understand what this means. This squared means that I'm taking the entire sine function and I'm squaring it. So there's another way to write it that may not look as clean, but it's the way that we have to do it if it's calculator or if it's something that's involving derivative. So let's rewrite it the way that we want to enter using our calculator. It'll be 95. Now in the calculator, it'll look like this. Okay, we got to use x instead of t. I'm using brackets here, but in the calculator, you can only use parentheses. It just looks a little bit cleaner on paper if I use brackets. Okay, I want to make sure. Sometimes I see students get stuck at this point, not knowing how to enter this into the calculator. So I want to make sure that we understand that the squared means bracket squared or parentheses squared. Same thing here. R of t. In the calculator, you're going to write it this way. Okay, so part A says, is the amount of water in the tank increasing at time t equals 0? So we know that if we want to determine whether the amount of water in the tank is increasing or decreasing, what units are we looking for here? Will this be in terms of gallons, or will it be gallons per hour or gallons per hour squared? Right, amount of water increasing. So this is just what? Just gallons per hour. Yeah. Now, if it says, is the rate increasing? If you see the word rate and increasing, then it's going to be gallons per hour, right? But here, this is the amount of water increasing, amount of water decreasing. This is gallons per hour. So the units that we want is in the same units as W of t and R of t. So for part A, we don't have to rely on derivative or calculus. We can just rely on merging them together, right? So W of t is the rate at which water is entering. R of t is the rate at which water is leaving. So what can I do with these two functions to determine whether the water is increasing or decreasing? Should we add or multiply or subtract. Yeah, we can, I think we should subtract, right? So if we subtract, we can figure out whether we get a positive number or a negative number. If we get a positive number, that means W of T is overtaking R of T. That means there's more water coming in than leaving, so the water is going to be rising, right? But if R of T is larger than W of T, then we'll get a negative number. If we get a negative number, then we know that the water level is decreasing, right? So we'll do RW of T minus R of T. Okay, so for this instance, it'll be W of 15 Now we can enter this in. If you're using 36 Pro, you will enter this in. Do everything by hand. You got to plug everything in yourself. But if you're using a graphing calculator, I encourage you to enter in your W of T and R of T under Y1 and Y2. That way, when we call these functions later, we don't have to keep entering them over and over again. Okay, so if you go to Y1, okay, 95 square root of x, parentheses, sine of x over 6, parentheses squared. Same thing here. Y2, I'm going to let the Y2 hold my R of T function. So 275, parentheses, sine of x over 3, parentheses squared. Okay, so I'm going to go back to my home screen because now that I have Y1, Y2, I'll just say Y1. Okay, so let me enter this in again so you can see every step I'm doing here. So if you look on the board there, vars, y vars, function y1, that will take you to allow you to call that or find that function y1. So vars, y vars, function y1, that's holding my W of T. And I'll do parentheses 15, and that's just, the calculator is going to enter in that 15 in for every variable in my W of T expression. Okay. Minus vars, y vars, function y2, 15. So that negative number tells us that W of T is larger than W of 1, or sorry, R of T larger than W of T, which means that there's more water leaving than what's coming in. So we expect that water level to be decreasing. Okay, part B. To the nearest whole number, how many gallons of water are in the tank at t equals 18? So this is the theme of these antiderivative word problems. It's always going to kind of have this kind of a formula to it. And let me kind of share that formula again. And it's always going to show up in some capacity. So any total amount that I'm looking for, okay, is the initial amount. There's a couple of moving parts here. If I want to find the total amount of anything, especially if there's initial amount and then amount coming in and amount removing or amount removed, it's going to look like this: plus the amount added minus amount removed. So if we can figure this out, we can figure out how much is in the tank or container at any given time. Okay, so let's build the equation first, and then we can do it for this specific case. So I will use A of t to represent amount. Okay, the initial amount, which is what? 1,200. The amount added. Now, amount added is in terms of gallons, so we have to make some adjustment, right? We can't just say W of t, because W of t is in terms of gallons per hour. So what do we have to do to get it into amount, into something in terms of gallons? We have to involve the what? Okay, integral, right? Because integral will allow this W of t to rise up to something in terms of the units that we want, which is in terms of gallons. So I need to do the integral from 0 to t of W of t. Now we'll use W of x. It's a little bit cleaner here because then there's no conflict of variables. We can actually plug this variable into this variable, so W of x. But we're referring to the same function. We're just giving a slightly different name so that the t will be able to insert itself in. Minus the amount removed. So the amount removed is also in terms of gallons. We want to make that gallons per hour to rise up in terms of gallons. So integral of R of x. So notice how right now I'm not putting 18 in for t because I want to create an equation that will give me that flexibility to adapt to any time that I want to have to involve in the future. So at least I have an equation that I can use for any circumstance. And then now let me use it for 18. So now I'll replace my t with 18 and I can solve for my specific case that I want to look for. Okay, so because I already have my W of x and R of x already defined under my y1, y2, I'm just going to go ahead and call it. So I'll say 1,200 plus the definite integral, so math 9, from 0 to 18. So I don't want to type in my entire W of x again. I'm just going to call it. It's under y1, so I'll go to vars, y vars, function y1 dx. Okay. Again, the keystrokes to get to y1 is up there on the board. Vars, y vars, function y1. Okay. So I want to subtract the amount that has been removed from the tank. Math 9 again. Oops. Vars. Okay. Part B says round to the nearest whole number, so we'll say 1310. So that means 18 hours in, taking into account how much water there is to begin with, how much water has been added, how much water has been removed. 18 hours in, there's going to be 1310 gallons in the tank. Okay, part C. At what time t is the amount of water in the tank at an absolute minimum? Okay, so that's kind of a giveaway here. What's involved here? If I want to find absolute max or absolute min, EBT, yeah. So this is an indication that we're going to apply EBT. EBT says test what? Endpoints and critical points. Okay. So critical points is where the derivative is equal to 0. So let's go ahead and find that. Okay. We know the derivative is going to come from this AFT equation. So let's build the derivative first. A prime. Right, critical points comes from A prime, where A prime is equal to 0. So let's look at every term here and see if we can find the derivative of each term. 1200 becomes what? 0, okay. And what happens if we find the derivative of this expression? Cancels out, and I'm just left with, yeah, W of t, yeah. So the derivative, it's going to wipe this integral notation out, and it's also going to wipe this notation out, but along the way, it'll just reinsert the variable back in. So 0 for 1200. Integral will come down to W's level, and then the integral of R will come down to R's level. Okay, so we're going to apply EBT. Critical points means I have to look to see where my W minus R is equal to 0. So we're going to test endpoints and critical points, right? EBT. We know the endpoints already, 0 and 18. We'll come back to it. Let's find our critical points. So because we have such a complex function, we're not going to solve it by hand. We're going to make the calculator do it for us. So we're going to do this. We're going to graph this. And we're going to look for the what? Yeah, look for, well, not intersection. I mean, we could say W of t equals R of t and look for the intersection, but I think this is a little bit cleaner. If I do R of WT minus R of t, I can set equal to 0, and 0 means I'm looking for what? What does 0 mean on the graph? Good, x-intercept. I think that's a little bit cleaner rather than having to search all over the graph to see where the intersection is. It's a little bit cleaner to look for the x-intercept. Okay, so let's practice entering that in. Let me do the graphing calculator first. Now I already have R of t and W of t under y1, y2. I don't want to, I could retype everything in and do 95 root x sine x over 6 minus 275, but I think it's easier if we just go ahead and have y3 represent the graph that we want to look at, and I'm just going to call y1 minus y2. Okay, that way I can avoid having to type everything in again. However, I'm going to make an adjustment here. I'm going to go to the equal sign. I'm going to unhighlight my y1, y2. I still want the function to be here, but I don't want it to show up on the graph. So anytime you unhighlight or highlight the equal sign, then you can choose which graph to show up on when you hit graph. Okay, I'm going to graph y1 minus y2, and I'm going to look for the x-intercept. Now, when I do this, let's start off. I want to show you if I like to always start zoom 6. It gives me the kind of negative 10 to 10 window, kind of like a standard window to begin with. And if I hit enter, a lot of times it's not going to be in the proper window that will allow me to see everything. I do see that vertical line. That vertical line just basically says that I'm zoomed in too far. Okay, it's not because it's a vertical line, it's because I'm zoomed in too far. I want to zoom out so that I can see the curvature a little better. Now, if you hit zoom out, you're really not going to have any control in terms of where zooming out. It's not very, it doesn't pinpoint where you want to look at. So I think the cleaner way is to go to Windows and then just play with the values yourself, right? Now your x-min, x-max is your t-value, and your t-value is only going to go between what and what? Yeah, 0 and 18. I like to see a little beyond my endpoint so that it doesn't feel like my graph is disappearing to the edge of the screen. So that's just my preference. I like to go a little to the left and to the right of my x value endpoints. You don't have to, but it just feels better to know that, okay, is it getting cut off, or is that the end of the graph? And then x-min, x-max, y-min, y-max, a little bit of a guessing game. Something that helps is you look at the coefficients here and you see that, okay, this is in the hundreds. So I probably need to be in the hundreds because these graphs are going to be really, really high and really low. So I'm just going to guess some number here. It's trial and error here. I'm going to say negative 200, 200. And if something doesn't quite look the way you want it to, you can just come back and just change those values. You're only playing with these four numbers when you're graphing. Okay, all right, hit graph. Let's see what happens. Okay, I'm not seeing the top of the graph, but I don't really need to, right? I only care about finding those x-intercepts. So as long as I see a good curvature, I know I'm not gonna have too hard of a time tracing the graph. Okay, so from here, I'll do second trace, and I'm gonna look for my x-intercepts. So I'm gonna highlight 0 and hit enter. And I'm gonna scroll my calculator or scroll my cursor to a point to the left of the x-intercept. I'll hit enter. I'll scroll to the point on the other side of the x-intercept, hit enter. Hit enter a third time. And that'll give me one x-intercept. So 6.495. We'll round to 3 decimal places. There's another one that I need to find, so I'll test that point as well. Scroll to where my other x-intercept is. I'll hit enter once to lock that point in, and I'll scroll to the other side of the x-intercept, hit enter again. 12.975. Okay. Okay, so now I'm just going to spend the time to test each of these points, 0, 18, 6.495, and 12.975, all into my AFT equation. I already built my AFT equation. So this is how I'm going to get to how much water is in the tank at each of these moments. And then I'll test all these points, and I can figure out whatever is the lowest amongst these candidates will be my absolute minimum. Let me see if I can get these critical points to show up on the 36 Pro. Okay, go ahead and try this. You know you're testing these 4 points against your AFT, right? Yeah, and then make sure you're in radian mode, right? Otherwise, the graph is not showing up. We're always in radian mode. So So we're just entering this in one by one, and we know A of 0 and A of 18. We already kind of found those over the course of the problem. It's just the 6.495 and 12.975. Okay, 525 and 1697. We're looking for the absolute minimum. The absolute minimum is going to be here at 6.495. Okay. Part D. Okay, for part D, it says for T greater than 18, so after 18 hours, no more water is pumped into the tank. But water continues to be removed at a rate of R of T until the tank is empty. Let K be the time at which the tank becomes empty, right? But do not solve an equation involving an integral expression that can be used to find the value of K. So we just want to figure out how long will it take for this tank to completely drain of the water that's inside the tank. So we know that how much water is in the tank 18 hours in. Or how much water needs to be drained from the tank. Because we know there's no more water pumped in the tank, so how much water is in the tank 18 hours in? Yeah, we know this is the amount, right? So we know that this is the amount that the tank has to drain if it has to go to empty. So we only have to worry about R of T. Oops, sorry, 1310. So it's only asking us to create an integral equation, and this is sufficient. Okay, we want to solve for K, the integral from 18 to K of R of T. We want this, however long it's going to take for this amount to be drained from the tank. We know R of T is the rate at which the tank is getting drained. The integral will tell us the amount, right? So we want this amount to total to be 1310. Okay, let's look at page 10. Okay, there's no snow on Janet's driveway when snow begins to fall at midnight. From midnight to 9 a.m., the snow accumulates on the driveway at a rate modeled by F of T. So we know that this is not the amount of snow at any given time. This is just a rate, okay? In cubic feet per hour, where T is measured in hours since midnight. Janet starts removing snow at 6 a.m. The rate G of T in cubic feet per hour at which Janet removes snow is given by this G of t. Okay, so let me talk about what this G of t means. G of t is in terms of cubic feet per hour. So this is the rate at which Janet is removing snow over the course of this time period. Okay, so she's working at different rates here. So from midnight to 6 a.m., she hasn't started, so her progress is 0. Between 6 and 7 hours, what is she going to accomplish? What does that 125 tell us? Right, cubic feet per hour. So that means between 6 and 7 hours, between 6 a.m. and 7 a.m., she would have removed how much snow? Yeah, exactly 125 cubic feet, right? So that's her progress between 6 and 7 a.m. She continues working from 7 to 9 a.m., but you can see that her progress slows, right? She's not working as fast as she began. She's still making progress, but slower than before. So she's only getting in 108 cubic feet per hour rather than her initial 125 cubic feet in that first hour. Okay, so just so that we know what those numbers mean. Okay, part A, how much cubic feet of snow has accumulated on the driveway by 6 a.m.? Okay, accumulation of snow. So this is how much is falling here. So which equation are we going to be using if we want to find out the accumulation of snow on the driveway? F of t or G of t? Yeah, F of t, right? Now, can I just plug F of 6 and figure out how much snow has accumulated? Okay, I have to involve what? Integral, right? I got to figure out how much snow from 12 a.m. all the way to 6 a.m. So I need to accumulate that rate over the course of a 6-hour period. I'm going to have to rely on integral. Okay, so 0 represents midnight. So from 0 to 6. Again, you're going to be using radian mode, and then the variable you're using is x. Okay, so enter this in the calculator and see if you can get it down to a number. Okay, 7x e to the cosine of x from 0 to 6. Okay, I got 142.274. And what's our unit going to be here? Cubic feet, right? Okay, part B, find the rate of change of the volume of snow on the driveway at 8 a.m. So rate of change of volume of snow, we want this in terms of cubic feet per hour. So we can just rely on F of t and G of t, right? So what can we do between these two if I want to find out the rate of change of the volume of snow at the driveway? Yeah, let's subtract, right? So we can figure out the rate at which snow is falling at 8 a.m. and the rate at which Janet is removing snow from the driveway at 8 a.m. and subtract those two, right? If one is greater than the other, then we know whether the amount of snow is rising or falling. So we'll do F of 8 minus G of 8. Okay, enter that in the calculator. Okay, so what does this number tell us in terms of what's happening on the driveway? Right, so we see that Janet is working at a faster rate than the rate at which snow is falling. Right, so she's making progress. So what's happening is the amount of snow on the ground is decreasing by this rate because of the work that she's putting in. Right. Okay, part C. Okay, let H of T represent the total amount of snow in cubic feet that Janet has removed from the driveway at time T after midnight. So here we're just looking at how much Janet has removed. We're not looking at how much snow is falling at that moment. We'll deal with that later. H of T is just focused on the progress that she's or how much she's able to remove. We don't care about how much is on the ground. Okay, so but we do know that she's working at different rates. So if I want to figure out how much snow she's removed at any moment in time, whether 6.5 hours or 7.5 hours or 8.5 hours, we got to create a piecewise function, right? We have three different scenarios. She's working at different rates at these different times. So it's a similar formula. It's still total amount equals initial amount. But now we don't care about how much snow is being added. We just want to know how much is being removed. But now the total amount that we care about is the total amount that she's taken out. Okay, so how much progress she's made, and how much more she's able to remove. So we don't have to worry about 0 to 6. Between 0 and 6, there's no progress. So we can start our problem at 6 hours in. Okay, so we're going to create an equation for what's happening between 6 and 7 hours, between 6 a.m. and 7 a.m. Initial amount, the initial progress, she hasn't made any progress. Even though there's snow on the ground, we're talking about how much she's removed. So she hasn't removed anything at 6 a.m. Sorry, let me make this a little bit more clear here. The initial amount is at 6, right? So from 6 to 7, she hasn't done anything at 6 a.m. But then from 6 to 7, this is the progress she's making. From 6 to T, and I want to use T here because we're not just looking at hour increments. We could be looking at 30-minute increments. What's happened by 6:30? What's happened by 6:45? Right. So what's the progress that she's making from 6 to 7 a.m.? Yeah, 125. Right. So we take the integral of 125, and this will tell us exactly how much progress she's made at any time between 6 and 7 a.m. Okay, we know that at the end of the hour, she's going to be able to get 125 cubic feet, but what's happening between 6 and 7? Okay, so we go through power rule here. 125 becomes, that's derivative. So integral is 125 what? Yeah, 125x or 125t. Yeah, let's just say x. This should be dx here. Okay, so 125 is a constant. Constant becomes a linear, and then we can plug in our upper and lower bound. Okay, I don't have to multiply this out. I can just make it a little bit cleaner here. 125t minus 6. So we know that this is the progress that she's going to be able to make if we enter any t value between 6 and 7. And we know h of 6 is 0, so don't have to worry about that. That's just going to be 0. Now, between 7 and 9 hours, she has a different rate, right? And what's her rate between 7 and 9 a.m.? 108. No. Same process here, 108x between 7 and t. But what's h of 7? How much has she removed by the time we check in on her at 7 a.m.? Exactly 125, right? We know that that's what she's doing, right? 125 cubic feet per hour. So that means by 7 a.m. she would have accomplished 125 cubic feet of snow. So it'll be 125 plus 108 t minus 7. So this is her progress at any moment in time. We know that between 0 and 6, nothing is happening. But then from 6 to 7, if I want to figure out exactly how much how much snow she's shoveled, we can plug in any value between 6 and 7, and we will get this. We'll be able to figure out what she's done. And then the 125 plus 108 t minus 7 is what she's able to do from 7 to 9 hours. Anytime I plug in, I can figure out exactly what she's done. Okay, so now part D, how many cubic feet of snow are on the driveway at 9 a.m.? So now we're going to go back to that formula that we've been using from the previous problem. Initial equals, total amount equals initial plus amount added minus amount removed. Okay, initial is 0. The amount added is from 0 to 9 of f of t. And then the amount removed is just h of 9. And h of 9, we've already built the equation to figure out exactly what she's able to accomplish. So we enter this in the calculator. We enter 9 into this formula. So we know that at a of 9, there's going to be 26.334 cubic feet of snow on the ground. Or sorry, on the driveway. Okay, your homework will be pages 11 and 12. I'll send out a reminder this afternoon. Thank you.